Hello student, today we will discuss Newton's second law of motion. So first we will discuss linear momentum. Linear momentum represent with small p. It is a physical quantity which is possessed by every moving object. When an object of mass small m is moving with velocity v vector, then linear momentum of object is defined as mass multiplied with the velocity of the object. That is, p is equal to m into v vector. It is a vector quantity and its direction is same as the direction of velocity of the body. The SI unit of linear momentum is kilogram meter per second. The dimensional formula of linear momentum is m1 L1 t minus 1. Case first, consider two objects each of mass small m. Suppose the two objects are moving with velocity v1 and v2 with v1 is greater than v2. Then P1 is equal to m into V1 and P2 is equal to m into V2. Therefore, P1 upon P2 is equal to m1 m V1 upon m V2. M to m cancel, or P1 upon P2 is equal to V1 upon V2, as V1 is greater than V2, so P1 is greater than P2. Thus, the linear momenta of bodies having equal masses are proportional to their velocities. This is shown by graphically. Here on x-axis v, on y-axis p. Then graph is straight line. Here m constant. Clear? Next, case second. Okay? Case second, consider a heavier object of mass m1 and a lighter object of mass m2. Suppose both the objects are moving with same velocity v, then P1 is equal to m1 into v and P2 is equal to m2 into v. Therefore, P1 upon P2 is equal to m1 upon m2, as m1 is greater than m2, so P1 is greater than P2. Thus, the linear momenta of bodies having equal velocities are proportional to their masses. That is, P is proportional to m, so that m increase, then P increase. Graphically, we can represent here on x-axis m on y-axis P, it is also straight line. Here V is equal to constant. Case second clear. Next case third. If two bodies of different masses have constant linear momentum, then the velocities of moving bodies is inversely proportional to their masses. That is, V is proportional to 1 upon m. So that m increase, then V decrease, and m decrease, then V increase. We can represent with graphically. Here it is m, here it is p. So graph is exponentially, here p constant. Clear? Okay. So Newton's second law. The rate of change of linear momentum of a body is directly proportional to the external force applied on the body, and this change takes place always in the direction of the applied force. If a body of mass small m moves with velocity v vector, then its linear momentum can be given by P is equal to m into v vector, and if force F vector is applied on a body, then F is proportional to dp vector upon dt, or we can write F is equal to k dp vector upon dt. Here dp vector upon dt is rate of change of momentum, and k is a constant of proportionality. Here k is equal to 1 in SI and CGS units. Then F is equal to dp upon dt, or F is equal to d by dt into m v vector, or F vector is equal to m dv vector upon dt, since A is equal to dv vector upon dt. Here it is acceleration produced in the body. Therefore F vector is equal to m a vector. Thus the product of mass of the body and acceleration produced in it is equal to the applied force on it, and the direction of acceleration is in the direction of force. Clear? Next, impulse. Impulse represent with I vector. The change in the velocity can be done by two types. First, by applying the force of large magnitude for a small time interval, and second, by applying the force of small magnitude for a long time interval. Thus, the change in velocity of the body depends upon the product of the applied force on it and time interval. When any constant force of small magnitude is applied on a body for a small time interval, then the product of force and time interval called impulse. That is, impulse is equal to force into time duration, or impulse is equal to total change in momentum. The total effect of force on the motion of a body is called impulse. It is a vector quantity and denoted by I vector. The direction of impulse is in the direction of force. Its unit is Newton second. Clear? If a force F vector acts on a body for short time interval dt, the impulse of the force is given by d I vector is equal to F vector into dt. If we consider a finite interval of time from t1 to t2, then the impulse will be I vector is equal to integration di vector, or is equal to integration from t1 to t2 f vector into dt. If f vector is constant, then I vector is equal to f vector integration from t1 to tt into dt, or I vector is equal to f vector integration of dt t limit t1 to t2, or is equal to f vector put the upper limit t2 minus lower limit t1, or I vector is equal to f vector into delta t. Here delta t is equal to t2 minus t1. Clear? Next, impulse momentum theorem. According to Newton's second law of motion, F vector is equal to dp vector upon dt. Therefore, F vector into dt is equal to dp vector. If in time 0 to t the momentum of the body changes from p1 vector to p2 vector, then integrating the above equation within these limits, we get integration from 0 to t f vector into dt is equal to p1 vector to p2 vector dp vector but integration from 0 to t f vector dt is equal to I vector. So we can write I vector is equal to integration of dp vector p vector and limit from p1 vector to p2 vector, or we can write I vector is equal to, first you put the upper limit p2 vector minus lower limit p1 vector. Clear? It is impulse momentum theorem. Thus the impulse of a force is equal to the change in momentum produced by force. If we plot a graph between force and time, the area under the curve and time axis gives the value of impulse, that is I is equal to area between curve and time axis. Clear? Example of Newton's second law of motion. While catching a fast moving cricket ball, a player lowers his hands. This is the reason for that initially the ball is moving and player applied a retarded force by his hands to stop the ball. Now if the player catches the ball suddenly, then a large force has to be applied to stop the ball due to the large retardation of the ball, whereby hands of the player get injured. When the player lowers his hands and catch the ball slowly, then retardation will be less. Thus, a small force has to be applied to catch the ball by the player, and the changes of injury to the player's palm will be less. Newton's first law gives the definition of force, while the Newton's second law determines the magnitude of the force. Clear? That's all for today.